All right, today we're going to tackle one of the most famous and efficient sorting algorithms out there, quicksort. It's incredibly fast, it's clever, and by the end of this, you'll get exactly what makes it such a powerhouse in computer science. Have you ever stopped to think about that? How your computer can take a massive, completely jumbled list of data and just sort it almost instantly? Well, a huge part of that magic often comes down to an algorithm, just like quicksort. So let's see how it pulls it off. So here's the game plan. We'll start with a quick introduction to what makes quicksort special. Then we'll dive into the absolute heart of the algorithm, the pivot. After that, we'll walk through the partitioning process step by step, see how recursion brings it all home, and finally, we'll break down its performance. Okay, so what is quicksort, really? And what makes it stand out from all the other sorting algorithms?
One of its biggest advantages pops right out when you compare it to another popular method, merge sort. You see, quicksort is an in-place algorithm. What that means is it does all its work directly on the original array, just shuffling things around. It doesn't need to create a bunch of temporary copies, which saves a ton of memory. That space efficiency is a really huge win.
To really get quicksort, you have to understand the one single concept that makes the whole thing tick, and that's the pivot. A pivot is just an element that we pick from the array to use as our reference point. The entire goal is to shuffle everything else in the array around this one chosen element. Now, you can pick any element you want, the last one from the middle, a random one, but to keep things really simple and clear for this explainer, we're always going to pick the very first element as our pivot. And this is the core logic right here. It's a simple, repeatable process. You pick your pivot. Then, you do some shuffling to get that pivot into the exact spot it would be in if the array were fully sorted. Once you do that, you've guaranteed one thing. Everything to the left of that pivot is smaller, and everything to the right is larger. This one operation is the key. All right, so theory is one thing, but let's get into the nitty-gritty. This is the partitioning process. This is how we actually get that pivot into its correct spot. Okay, let's walk through an example to make this real. Here's our array. And like we said, our pivot is going to be the first element, so it's 4. To get this thing partitioned, we're going to use 2 pointers. Let's call them I, starting right after the pivot, and J, starting at the very end. Their job is to scan towards the middle. So here's the dance. The I pointer starts moving to the right, and it's looking for the very first number it can find that's bigger than our pivot 4. So it skips the 1, and boom, it stops at 7. At the same time, J starts moving left, looking for the first number that's smaller than 4. It skips 8, and bam, it stops at 2. Now both of our pointers are paused. And since I is still to the left of J, the rule is simple. We swap them. The 7 and the 2 trade places. And look at that. Our array is already starting to look a little more organized. A smaller number moved left, and a larger one moved right. And now, we just do it again. From their new spots, I moves right and stops at 6, J moves left and stops at 3. And again, I is still to the left of J, so we do another swap. The 6 and the 3 trade places. So we try to do the dance one more time. I moves to the right, it stops at 6. J moves to the left, and it stops at 3. But wait a minute, look at their positions. I is now to the right of J. They've crossed paths. And that's our signal. That's when we know this search and swap phase is over. And here's the brilliant final move. Once those pointers cross, we take our pivot, that 4 sitting at the very beginning, and we swap it with the element where the J pointer ended up, which is 3. Now look at the result. Our pivot, 4, is sitting perfectly in its final sorted position. Everything to the left is smaller, and everything to the right is bigger. Mission accomplished. So, we've successfully put one element in its perfect spot. That's great, but how does that sort the entire array? Well, this is where the real genius of the algorithm comes into play, recursion. This strategy is called divide and conquer. Since our pivot is now in its final correct place, we can kind of just ignore it. It's done. And what we're left with are 2 smaller, completely independent sorting problems, the little array to the left of the pivot and the little array to the right. So what do? We just run the exact same quicksort process on each of those smaller pieces. And this just keeps repeating, breaking the problem down into smaller and smaller chunks until everything is sorted. So we know the process is clever, but the all-important question is, how fast is it? Let's take a look at the performance. Now, this table uses something called Big O notation to describe performance. All you need to know is that it tells us how the algorithm's runtime scales as the list gets bigger. In the best and, more importantly, the average case, quicksort is incredibly fast, at what we call nlogn. And its space complexity, how much extra memory it needs, is 1, which is just fantastic. It basically means it needs no extra memory. But you can't ignore that last line. The worst case is n squared, and that is dramatically slower. We have to understand why that happens. And that's not just some academic detail, by the way. Understanding why quicksort can have this terrible worst-case performance is a classic question in programming interviews, because it really shows if you understand what's going on under the hood.
So the worst case happens when our pivot choices are consistently awful. Imagine we get an array that's already sorted, and we keep picking the first element as the pivot. Every single time we partition, we'll end up with a subarray on one side that's totally empty, and a subarray on the other side with everything else. The divide and conquer efficiency just completely evaporates. It's no longer dividing the problem at all, and the performance tanks.
And that really leaves us with the core trade-off, doesn't it? Quicksort is incredibly fast on average and super light on memory, but it carries this small risk of a massive slowdown if you get unlucky with your data and pivot choices. And this makes you think like an engineer. When is that trade-off worth it? When does its amazing average speed make it the right tool for the job, despite the risk? It's a crucial question every developer has to think about.